All right, physics friends, we're going to get right back to the third law and summarize everything that we have said so far. The third law is most definitely the trickiest of the three. So let's remind ourselves what it says. It says if you're taking a look at the semi-major axis of a planet's orbit, which again is half the longest distance or longest diameter across, then that distance is proportional to the period of time, p, or period, to go around the sun. Now, just think about this for a moment. It would make sense that there would be a relationship between how far a planet is on average from the sun and how long it takes to go around. But it's not linear. You might think, oh, if it's twice as far, it takes twice as long. Not at all. It's not only not linear, it's not even really what you would expect under any circumstances. So that's why I think Kepler is kind of so amazing here, because it took him a while, but he figured this relationship out. He didn't have the advantage of a computer or calculator, or he didn't even have the advantage of logarithms, which is how we would do it now. So this work predates logarithms. So he did it purely by this brute force, graphing and trying lots of different relationships. So the relationship is a cubed is proportional to p squared. Now, that's where we left off, and I showed you a sample problem that I'd like to kind of go over again. Okay, so let me skip through this, and I want to talk about how we make this an equality. We make it an equality, a cubed equals p squared, if we choose smart units. That is, a unit that for when a is 1, then p is 1. So it works beautifully for the Earth. We just say that the size of Earth's orbit is 1 AU, or 1 astronomical unit, and that is the size of Earth's orbit, the size of the semi-major axis of its orbit, or again, that's close to the average distance between Earth and Sun, about 93 million miles, about 150 million kilometers, about 8.3 light minutes. And then we say the period of Earth's orbit is 1 year, 1 Earth year, which is about 365 and a quarter, or 365, just under 365.25 days. So we define things in terms of Earth. So again, Earth, we're measuring A in AUs, and we define an AU as the size of Earth's orbit, and then we define 1 year as the size of Earth's year. So this is the example I did last time. You have a near-Earth asteroid that happens to be 4 AUs in orbital size. Where that would be, let's see, if Earth happens to be 1 AU, then this asteroid would be 4 AU. So it actually wouldn't even be in this picture. It would be way over here, maybe on the edge, and orbiting, of course, the whole way around. So a cubed is p squared. We're going to plug some numbers in here for a and for p. Sorry, p is what we're going to calculate. So we get 4 cubed equals p squared. 4 cubed is 64, and p squared is just p squared. So p squared is 64, so p is the square root of 64, which is 8 years. Here's a crazier example. I want you to imagine Pluto. Pluto, the sadly demoted from major planet status a few years ago. So Pluto is about 40 AUs in orbit size. Now, 40 AUs in orbit size means that it's 40 times further away from the sun than the Earth is. So that that picture you see right there is not remotely to scale, unfortunately. 40 times further. That's 40 times, 93 million miles, or 40 times 8 light minutes. What's that make that? About 320 light minutes. Geez, it was. That's pushing 6 hours, right? It's over 5 hours for light to get from the sun to Pluto. Crazy. Okay, so doing the math. A cubed is p squared. Now, 40 cubed is p squared. What's 40 cubed? Glad you asked. 64,000. And if you take the square root of 64,000, you end up with about 250 years. That means it takes Pluto about 250 years to go around the sun once, which is sort of unimaginable. It was actually discovered in 1930. Since it was discovered, it's barely just made 1/3 of an orbit around the sun. That's just nuts. The picture you're seeing right there is a relatively recent photo, actually. So Pluto also has the greatest inclination to the Earth-Sun plane, or what's known as the ecliptic plane. Yeah. Pluto has this kind of very slanted orbit to the Earth-Sun plane. Now, exoplanets are worth talking about. I won't test you on this, but we are able to actually determine, in fact, in your lifetime, there have been hundreds of exoplanets discovered. That is, planets that go around stars that are not the sun. We have discovered thousands of these bad boys, really, in the last 25 years or so, since the 90s when they were first discovered. This is kind of hard to believe. I remember when 51 Pegasi, it was discovered, in 47 Ursa Major as well. Those are the first two there. And they were discovered. It was incredibly exciting. It was an exciting time to be in physics and astronomy. I will tell you that. But since then, with techniques that were advanced, well, there have been many, many more that have been discovered. But you know what? They still all obey Kepler's 3 laws. Now, Kepler's third law is sometimes called the harmonic law. I took this picture out of his book called The Harmonies of the Spheres. He actually imagined that the planets were orbiting around the sun at distances that were kind of very similar to how strings work. He kind of imagined that planets made music, going around the sun that would be pleasing to a creator. I always thought that was, just such an awesome idea. It's kind of kooky. If you read more about Kepler, you find out that he had lots of strange and kooky ideas. But, this is sort of a pretty nifty one. And, of course, sadly, there's no evidence for any of this. But, it's still a cool idea. A couple of closing thoughts from our boy Kepler. The laws of nature are within the grasp of the human mind. God wanted us to recognize them by creating us after his own image so that we could share in his own thoughts. Isn't that awesome? There's the Kepler telescope there off to the right. Whether you're a religious person or not, I just think that's kind of a cool way to imagine it as he did. So, Kepler, yes, my hero. Kepler actually was such a hero of mine that I named one of my cats after him. Now, the guy who lived at the same time in Italy was Galileo. His life overlapped almost directly with Kepler's, though they did not know each other. They wrote back and forth a couple of times in professional capacity. Galileo ends up living a few years later than Kepler does. Kepler dies in 1630. Galileo is just about to get himself into hot water right around then. There's Galileo's refracting telescope. So in the early days of Galileo's professional life, he invented this. Actually, it's probably more accurate to say that he kind of stole the idea. But, he adapted the idea. How about that? And he, in 1610, now it's 410 years ago, he published the Sidereus Nuncius, or the Starry Messenger. And in that, he published all of his observations with his telescopes that he just took really over a few days' time. So you can see his drawings of the moon. Also in the book, you find his drawings of his first observations of Jupiter, where he noticed that Jupiter seemed to have little stars of its own. And he actually had discovered the first 4, or the biggest 4 moons of Jupiter. So that was it for him. He was then convinced, because Jupiter had its own moons, and Jupiter went around the sun. Jupiter had its own moons that went around Jupiter. We have a moon that goes around us. There's no reason whatsoever why we can't imagine that Jupiter indeed is going around the sun, and the Earth is going around the sun. So that's all it took. Add to that reading Copernicus, and there you have it. So he discovered a whole lot of other things too. Craters in the moon, many, many, many more stars in the Milky Way galaxy, the phases of Venus, rings of Saturn, sunspots, a whole lot of other stuff. I like this image a lot because that's actually a drawing from Galileo. That's actually one of his tracings of sunspots on the sun. He's the first person to show that the sun actually rotated. He took, I think, 35 images of the sun and showed that it actually rotated, just based on the motion of the sunspots. There's his grave in Santa Croce, I think, in Florence. It's quite amazing. It's actually almost amazing that he has a grave, a marked grave at all, because by the time he was dead, he'd been excommunicated from the Catholic Church. He was a total pariah because of his belief that the Earth went around the sun. Now, he eventually recanted all of that, but still, nobody really believed his recanting. So he was under house arrest for the remainder of his life. It could have been worse, of course. And history has truly vindicated our man, Galileo. Here it is, his 1632 book, The Dialogue Concerning the Two Chief World Systems. He wrote it up actually as a dialogue between three men, and they were debating basically the merits of the Ptolemaic view. That's the Ptolemy's world that put the Earth at the center, and the Copernican world that put the Sun at the center. Well, it was banned. It was banned almost immediately. It doesn't help when you happen to live in Rome and you try and publish this literally in the shadow of the Vatican. So Galileo, it could have gone a lot worse for Galileo, but he spent his time in jail and then under house arrest for years of his life. But again, there could have been torture involved, so it could have been a lot worse. So anyway, we are fortunate to be the beneficiaries of the hard work of Galileo and Kepler, who really took one for the team, you know. And then Newton, who's just born a few months after Galileo dies. Newton sort of gets all the glory without really any of the suffering. What a bummer, huh? All right, friends. See you soon. See you on the moon.